Now I have discussed first order reaction in part 7, 8 and 9. Please watch those videos before you watch part 10. And now in this video I will concentrate on the first order reaction and will discuss all the features of it. Now if we represent a first order reaction as A arrow product, then we can proceed with two different ways. Now one way I have introduced you before maybe in part 7. Now that looks like this one. So we have considered the initial concentration to be C0. Now it is at the time of start. Now after elapse of certain time, the concentration of reactant that is remaining is C. So at this point, the rate of reaction is minus ddt of C, and this is equal to rate constant multiplied by concentration to the power 1. So this is the rate equation and it is in the differential form. Now this power 1 represents the first order reaction. Now another approach is that both are exactly equivalent but two different ways to represent the same thing. Now here we may start with the initial concentration A instead of C0. So we have 0 here. This is at the time of start. Now let us consider that after the elapse of certain time t from the start, X amount of reactant has reacted. So the amount of reactant that is left at time t is A minus X, and say here we have X amount of product. If it has a coefficient 1, then we can write X. So this is at time t. So you can compare these two approaches. You see C0 here is resembling A in this approach, and what is C, that is amount of A that is left after time t, is given by A minus X. Now the differential form of the rate equation is minus d of A minus X upon dt. So here it will depend on the concentration. It will depend on the concentration at time t. Here you must be careful that the rate will depend on the concentration, on that concentration at which you are measuring the rate. So if you measuring the rate at time t, then the rate will depend on this C. And if you measure at a different time, say t prime, then the rate will depend on the concentration of the reactant present at that time. So the rate must be proportional to the concentration at the time at which the rate is measured. So when we measure this rate, the concentration of the reactant is A minus X. Now here to the power 1 means the reaction is first order. Now here we have integrated in the video part 7, and this was like, this is just a simple rearrangement, and integrating, this is constant, it comes out, we have minus log natural C kt plus integration constant. Now when t equal to 0, that is at the time of start, we have C equal to C0, that is when the reaction has not started, the concentration of A was C0. So putting here we put here t equal to 0, so it is 0 and C equal to C0, so I is minus ln C0. So we have minus ln C equals to KT minus ln C0, or we have ln C equals to KT plus, we multiply both sides by minus 1. So we have ln C equals to minus KT plus ln C0. So this is the integrated rate equation for the first order reaction. Now here what we will have? Similar thing. Now after rearrangement we integrate. Now see, this and this one are same thing. So if we consider it as Z, so it is dz by Z. Like here it is dc by c. So this negative sign will have no impact. So we will have minus log natural A minus x equals to KT plus I. See you see that here we have minus ln C. Now C is the remaining concentration of A, and here A minus x is the remaining concentration of A. Now when t equal to 0, no reactant has been converted to product. So we have x equal to 0. So I equals to, here I equals to, we take this KT to the left hand side. So we have minus ln A minus 0, x is equals to 0. So minus ln A minus 0, and KT comes to the left hand side. So it is K into 0. So we have minus ln A. Now we put this in this equation, so that we have minus ln A minus x equals to KT minus ln A. Again multiplying both sides by minus 1, we have ln A minus x equals to KT. Here there will be a negative sign, it is ln A. So this is the integrated form. So if you compare the two results, you see these are the same thing, only the mode of representation is different. Only the mode of representation is different. Now you see that this is C, that is concentration of reactant at time t. This is also concentration of reactant left at time t, and it is minus KT, and this is the initial concentration. Here also it is the initial concentration. Now another form of this integrated rate equation is, here we take this to the right hand side and minus KT to the left hand side. So we will have ln C0 by C. Be careful, we are taking this one to the right hand side, so that will be ln C0 minus ln C. So ln C0 minus ln C will be ln C0 by C, and we are taking minus KT to the left hand side. So this will give this relation. Now ln x equals to, it is actually log E base x. Now we can write it as log x upon log E. Now we can write it as log 10 upon log E into log x upon log 10. So we are multiplying by log 10 and dividing by log 10. Now log x upon log E, it is log E x. So log 10 upon log E will be log E10 and it is log 10 base x. Now log natural x is log E base x. So log E base 10 will be log natural 10 and this log base 10 is symbolized as log x. Now ln 10 is almost equal to 2.303. So we have the relation between log natural x and log 10 base x. So the log 10 base x when multiplied by 2.303, it will give the log natural x. So another form of this expression is we convert this log natural to log 10 base. So it will be 2.303 log C0 by C equals to kt. Here also we can write in a similar way, or ln, we take this to the right hand side and take this to the left hand side. So we have ln a upon a minus x equals to kt. This is another form, and we have another form this one. Equivalent thing. Now we have to plot the two results. So let us try to plot log. First let us try to plot ln C versus time. So we are trying to plot ln C versus time. So we intend to show the variation of log natural of the concentration of the reactant over time. Now for this we must use this equation, since this gives us the variation of log natural C with time. Now you can see that this equation is actually resembling the equation of a straight line. Here C is the intercept, not the concentration. It is the equation of a straight line. So you can see that this x is t here, and this y, this is ln C, and the slope it is given by minus k, and this is the intercept. So we will get a straight line with a negative slope. So it will start from this point, and so at t equal to 0, ln C will be ln C0, and we will have a straight line that will fall with time. So we get a negative slope. Now the slope is given by, we measure the angle theta here, slope is given by tan of theta, and that upon correlating we have this slope to be minus k. Now if after experiment you get data points of time versus concentration, then you take the log natural of the concentration and plot it over time. You will see that you will get a straight line with a negative slope, and after measuring the angle theta you take tangent of it, so that will give you minus k. So from experiment you can draw this graph, and from this graph you can have the value of rate constant for the reaction. Now there is another way to obtain the rate constant for this reaction, for any reaction, that is you get the data of variation of concentration, you measure the initial rate for various concentration of the reactant, and you determine the order which I have shown you in probably part 2 or 3 video. Please watch that video. Now when you get the order of the reaction, you put the value of the order and the initial rate in the rate equation, then you will have the value of k. So there are two ways to have the value of rate constant. So when you use this equation, it will give you a straight line with a negative slope, and from the slope you can have the value of the rate constant for the reaction. Now if you replace it with log 10 base, so it will start from log 10 base. In that case, the slope will be minus k by 2.303. Since if you convert this to log, then you will get 2.303 here. You will also get 2.303 here. So that will cancel out. And when you divide 2.303 both sides, here it will be minus k by 2.303. So the slope will change, but k will remain constant. Now I have noticed in my teaching career that higher secondary students often forget during exam that which one will be in the numerator between C and C0, which one will be in the numerator and which one will be in the denominator. There are some problems which start from this equation, and at examination there is no need to derive this equation. So if you can memorize this equation, then you will be able to do the problem. But they cannot memorize, they can memorize the structure, but they forgot what will be in the numerator between C and C0. So here I will suggest you to check a simple logic, that this is the concentration after start of the reaction. So as the reaction proceeds, the concentration of the reactant will fall. So the maximum limit of C is C0. The maximum value that C can attain is C0. So C is always less than equals to C0. Now if you have a fraction where the numerator is always greater than equals to the denominator, so this fraction cannot give you less than equals to 1 value. So the fraction is always greater than equals to 1. And if within the parenthesis of logarithm, if you have fraction greater than 1, it is always be positive. Now rate constant is positive, t is positive. So to have this value positive, the greatest value, that is the initial concentration, must be in the numerator. Through this logic you can memorize the formula. Now if you try to plot this equation, then what will happen? Same thing. Here you just write ln a minus x instead of ln c. Now it will start from ln a. See, this is the intercept and this is the time. So you get a equation of a straight line, y equal to mx plus c. So here also you will get a straight line with a negative slope. So the same thing. Now in part 8, I have shown you that the half-life of a first order reaction is independent of C0, that is the initial concentration. The half-life of a first order reaction is independent of the initial concentration. Now, what is half-life? Half-life is the time required, it is the time required for 50% completion of the reaction. So if we start with 1 mole per liter, then the time required for 50% completion, that is when there will be 0.5 mole per liter left, then we can say that the reaction has experienced a time travel of half-life. So after one half-life, we have 50% of the initial concentration to remain left to remain left in the reaction vessel. Now what about the half-life of a first order reaction? We got that half-life of a first order reaction is equals to 0.693 by K. So here you are not getting the expression of C0. So it is independent of the initial concentration. Now it is dependent on the rate constant. But rate constant is definite for a particular reaction at a definite temperature. So as long as temperature is constant and you are performing an experiment with a particular reaction, so K will remain constant. So you have a definite half-life. Now say for an example, this T half equal to 20 minutes. So after elapse of 20 minutes from the start, this 1 molar reaction, this 1 molar concentration will be converted to 0.1 molar. Now the beauty of the first order reaction is that if you wait for another 20 minutes, that is another T half, if you allow another T half, you will see that there will be 0.25 molar left. So the time required for 50% completion starting from 1 molar to 0.5 molar is same as when we start with 0.5 molar and we get 0.25 molar. So the time required for 50% completion is independent of the initial concentration. Whether we start from 1 molar or we start from 0.5 molar, it is completely independent. This is the beauty of a first order reaction. You have to be able to derive the expression of half-life, which I have shown you in part 6 and part 8. Now I have written a form of the integrated rate equation. It looked like this: ln C0 by C equal to kT. Now here we have C0 by C equals to e to the power kT, or rather change it first. So what we have done, we are changing the fraction within the log natural. So if we replace it by C by C0, then here will be a negative sign, so we have minus kT. Now if we take out the logarithm, we have C by C0 equals to, since this is log natural, it will be e to the power minus kT. So C will be equals to C0 into e to the power minus kT. Now this is an important relation which is obtained from the integrated form of the rate equation for a first order reaction. This is for first order reaction only. Now here, if we plot C versus T, we can see we are plotting here C instead of log C or log natural C with time. So it starts from the initial concentration C0 and it falls exponentially. You see, it falls exponentially. Now why we try to draw graph? Is this because graphs can be plotted? No, it's not the case that graph can be plotted only. Actually, what this equation is carrying, what information this equation is carrying, this graph can also carry the same information. So we can say that graph speaks. A graph or a picture can speak in the same language which an equation speaks. So what I am trying to tell you is that we have noticed just now that half-life for a first order reaction is a constant and it depends on the rate constant only. Now what is half-life? it is not to scale. See, if this is C0, then this is C0 by 2. So the time required for this 50% completion will be T half. So this segment we can call it as T half. Now for passing of another half-life term, we will have the C0 by 2 to be converted to C0 by 4, since after passage of the first half-life 50% is remaining of C0 and we are attempting the passage of another half-life. So 50% of this one will remain left, so that will be C0 by 4. Now you see from this graph, you see this is T half. Now for another term C0 by 8, you see, so this is another T half. So from this graph you can notice that this length is equal to this length. So this length is equal to this length and it is equal to this length. So T half, what it is giving you, the message it is giving you that T half for a, that is half life for a first order reaction is constant. Now in the next video I will discuss with the second order reaction, the topic second order reaction.